Christian Binek, who is the Charles Bessey Professor of Physics at the University of Nebraska in Lincoln. And he's the director of the Nebraska Nanoscale facility, the NNF, and that's one of our fellow NNCI sites. He received his PhD from the University of Duisburg, and he is also serves as the scientific director of a new NSF-sponsored EPSCoR program entitled Emergent Quantum Materials and Technologies, or EQUATE program. So I will now turn it over to you, Christian.
Okay. Thank you, Pat. And let me start with the standard question. Can you see the first slide?
That's good.
Okay, right. Thank you. Well, it is certainly difficult to follow up on this wonderful presentation from Mark and all the great presentations we heard today so far. But I try my very best to inform you about those activities in the Internet of Things, Nano Internet of Things we do at the Nebraska Nanoscale facility. Let me start by saying that the Nebraska Nanoscale facility itself is basically an outgrowth out of the larger Nebraska Center for Materials and Nanoscience we are fortunate to have here. And as has been mentioned before, we are, of course, group of that 16 sites that constitute the NNCI. And we geographically occupy here this center of the United States. So we serve the western part of the Midwest, basically. Our core facilities are located in this building here at the University of Nebraska, Lincoln, in the Wojtek Nanoscience Research Center, 32,000 square foot for our facilities. And this is a slightly outdated photo of the group of people that are at the heart of NNF. Let me say also a few words about our capabilities in terms of fabrication and characterization. I don't go into any details, but very briefly. So we have 6+2, I would say, core facilities here, the nanomaterials and thin films. This little image you see here is a wonderful pulsed laser deposition system I use myself quite a bit. Then we have a clean room with optical and electron beam lithography and dry etching capabilities. We have electron nanoscopy. Here you see our flagship at 200 kilo electron volt electron microscope, the OSIRIS. And then we are very well equipped with scanning probe microscopy that goes all the way from atomic force microscopy, magnetic and piezo force microscopy. And not very recently, but some time ago, it's our newest machine is an AtoCube system that is another very versatile scanning probe microscope that allows us to go to low temperatures and also apply magnetic fields up to 9 Tesla. We have physical characterization properties. Here you see a quantum design squid. We have multiple X-ray structural characterization machines, small angle, wide angle, and powder, all these things. And then with these two centers, we have access to 3D printing and additive manufacturing. And here we have access to NMR capabilities for molecular characterization. And all these core facilities are so to say supervised and maintained and by a PhD holding specialists who take also care of our users. So with that said, let me directly go into what we enable in terms of nano IoT here at the University of Nebraska Lincoln within NNF. And I think I can group these basically into two categories which we pursue in this regard. One is under the umbrella of information technology, and the other one is along sensing applications with some overlap between the two. So let me start on this side. As we heard many times today, that ultra low power of devices, in particular memory and logic devices, is certainly a very important feature we want for these components, IoT components. So that is another umbrella that then breaks down into two parts I want to talk about a little bit in more detail. On one hand, spintronics, and here particularly antiferromagnetic spintronics. And I will actually give you an example here of my own group. And then nanoelectronics with the emphasis on variable, or at least platforms for variable electronics and flexible electronics. And then I also will report about a micro electromechanical system, MEMS, that is used to realize a rudimentary form of a neural network that does basic types of computation, and is also addressing the possibility of variable electronics and energy efficiency there. And then these sensing applications, again, here we have, one could say, first rudimentary quantum technological devices. Here in open gate field effect transistor, I will report about that. That is based on electron tunneling between gold nanoparticles. And then finally, I give an example about a nanophotonics, a very active area here in electrical and computer engineering. And I talk about something somewhat related to what Mark was reporting at the end, namely light matter interaction with metamaterials and with metamaterials that have chirality, and therefore you have a dichroism here between left and right polarized light that can be used in various ways. Okay, let me start with the information technology applications, and here particularly with the ultra low power umbrella. And here then I start with antiferromagnetic spintronics. A few words about what that really means. So not everyone might be familiar with spintronics. That is an artificial word that is basically made from starting from electronics. So, and when you replace the electron, so to say, by the spin degree of freedom, then you have a new type of tronics, the spintronics, that can be used to make devices. Now, why is that useful? It is useful because it is inherently a non-volatile, something that is also very beneficial for the Internet of Things applications, especially if you have not a single spin you operate with, but if you have collective interacting spins that create some form of magnetic order, then you can easily have non-volatility, and that means if you switch off devices, they keep their state in the memory. So energy efficiency is key for advances in this field of electronics. We have heard it today many times. Here, just a dramatic example, maybe already a little bit outdated, but that makes the problem, brings it basically to the point. So that was IBM's Watson. You may remember that a couple of years ago, the machine that was able to be victorious in this game of Jeopardy against the grandmasters, and that was an impressive feat, of course. But what I want to point out here is the energy consumption. So that machine needs to be hooked up to a power outlet and consumes 85,000 watts. And if you consume that, compare that with the competitors, human brains, they operate on a level of 20 watts. So you see a gigantic gap here where modern electronics still has room to vastly improve. So energy efficiency is, of course, important for the Internet of Things, maybe even more so than speed. And part of it is, of course, we need energy supplies, as again we have discussed today many times. And also the non-volatility is important. You know, if you want to make certain components, I know my desk, for example, if I want to make it an intelligent device where I can store information and write on or something like this, I need memory that is not losing its information when I turn it off for a long time, and spintronics can do that. Now let me also say a word about this antiferromagnetic component that has also advantages. Again, it can have an advantage of going closer to energy efficiency, but primarily it's in fashion because it allows devices that can be ultra fast. We could go from the gigahertz bottleneck of ferromagnetic spintronics to potentially terahertz, simply because the Larmor precession frequency is here not, which determines the speed of the reversal of the order parameter, is basically given here by the effective field given by the interaction rather than by the applied field, and that can switching speed up. Okay, now let me go into an example. This first example is actually an example that comes from my group in collaboration with many others here at University of Nebraska and elsewhere. And what we did is we took a magnetoelectric material, in this case, the chromium oxide, an antiferromagnetic insulating material, and we doped it with boron. And by doing so, we dramatically changed its properties in such a way that we are now able to switch by 90 degrees the Néel vector or the antiferromagnetic order parameter only by applying an electric field, a voltage. We do not need an external magnetic field to do that. And that is very advantageous for this type of devices. And what you see here is basically the proof of this claim. So this is a Hall bar type device. So we put a Hall bar structure on top of this antiferromagnetic thin film. Here you see the optical image of the lithography we did at NNF. And then we drive a current in this direction and probe the transverse Hall signal. And we probe the Hall signal in particular in response to a gate voltage that we apply across this antiferromagnetic film. And then you see we can switch the Hall voltage between two states, a state of low Hall voltage and a state of a significant Hall voltage. And that switching is non-volatile and is done in response of an electric field only. There's no magnetic field needed to switch between these two different states. And here you see a AFM and MFM images of this Hall bar structure. And I'd like to point out here in particular the MFM data, which show that indeed application of a voltage changes the underlying magnetic or magnetization distribution, an independent evidence that this is indeed a magnetic switching phenomenon. And these devices have another advantage. So we switch here the order, the antiferromagnetic structure by a voltage only and not by a current. And because currents are always accompanied by a Joule dissipation, this is a nice pathway to ultra-low power electronics. The next example comes from my colleague Xia Hong from the Department of Physics and Astronomy. And what she and company did was they grew heterostructures out of two-dimensional van der Waals materials, here in particular the uranium disulfide material. And this material is a two-dimensional material, and because of the van der Waals bond, you can peel it off, very similar to what you do with graphene. The point being here, if you grow this ferroelectric polymer, PVDF, on top of this 2D material, then this polymer can be grown into nanowires of, here in this case, of 10 nanometer width. And the interesting part happens when you now apply a voltage across this device. Here is again a transistor type structure made out of this van der Waals material and the polymer on top. And you can measure a source drain current in response again to a voltage across the device. And what you find is that the polarization state of the ferroelectric material dramatically changes the current that is transported by this van der Waals material. And you see that here in this graph. So you get basically a contrast of on the order of 10 to the power 8. So 8 orders of magnitude difference in the current, depending on whether the polarization of that ferroelectric material is up or down. And again, that is a switch, a non-volatile switch potentially that you can use for transistor type applications, for example. And the important point here being that these materials, the polymer, the ferroelectric polymer and the van der Waals material, they are flexible, and this enables a pathway to flexible electronics. I mean, obviously, this is not there yet if you grow it on this type of substrates, but the action happens here, and this is flexible material for potentially flexible electronics. Another example comes from, again, a colleague, Fadi Al-Salem, from the Architectural Engineering and Construction Department. And he works on MEMS. And what he does is he creates basically a very rudimentary form, a proof of principle form of a neural network that is made out of these mechanical oscillators that are realized here in this micro electromechanical systems. And what he does is he couples masses as oscillators in a non-linear way. So here's the possibility to implement a non-linear coupling. And by this non-linear coupling, he then can create a kind of a neural network mapping. And what this simple computer achieves is it can, for example, distinguish different types of input voltages. It can identify if a voltage is smooth, let's say sinusoidal, or a zigzag type of excitation. It's a proof of principle, and again could lead to some form of variable electronics where energy can be harvested from motion, for example. Then another example comes from a colleague, Ravi Zaref, again here at UNL, from chemical and biomolecular engineering. And this is an example that can be looked at as a simple form of a quantum technological device. It is again a transistor structure, in this case a particular open gate field effect transistor, and the channel that can be made conducting or less conducting is a nano in the following sense. It is a network of gold nanoparticles that you can see here in a sketch and here in a scanning electron microscope image. And now, depending on the gate voltage, he can change basically how many of these particles are included in a percolating network that connects them via tunneling. So there's electron transport via electron tunneling possible, and whether particles belong to that chain of gold particles that contribute to this conducting network depends on the gate voltage, because the gate voltage allows to adjust the Fermi levels. And what he is particularly proud of to mention is that this electric behavior of this type of transistor is not, that's the whole point here, is not the phenomenon of Coulomb blockade. And it's a subtlety in the sense that the IV characteristics of this material very much look like Coulomb blockade. But what he finds is that he can basically scale all these curves. He can create a data collapse of all these curves, which means that these two parameters here, the threshold voltage and this critical exponent here, they are independent of the gate voltage. And in the case of Coulomb blockade, that would apparently not be the case. So there's interesting physics in the electron transport here, but one can also look at applications, of course, and in that sense, it is a living transistor, if you like, or at least one of the applications can be looked at it that way. This open gate geometry of this field effect transistor allows you to put all kinds of things here on top of this open gate, and you can, for example, use algae cells and then shine light on these algae cells, and of course they do what plant cells do. They do photosynthesis, and that apparently changes their cell potential, and that cell potential then has an effect as gate voltage and can be sensed by the field effect transistor in terms of turning on or off a significant source drain current. And here you see on off means light on or light off, exposing the algae by light or not, and that's a nice kind of application. So a connection that allows you to investigate cells and cell responses on stimuli with the help of a field effect transistor. And my last example comes from basically from the Department of Electrical and Computer Engineering here, Christos Agriopoulos and Eva and Matthias Schubert and company. It's a long list of collaborators, but all here from electrical and computer engineering. They work on this helical nanophotonic metamaterials. So what they basically do is they fabricate materials by a method we heard about earlier today, by glazing angle deposition, and then rotating the substrate. They are capable of forming these spirals on top of a substrate, and these helical structures have a chirality. Here again, you see briefly explained the concept of chirality. The nicest way to picture is by the mirror image of a hand that you just cannot superimpose. So that would be an example for an object that has handiness or chirality, and obviously, intuitively, it is already clear that such a structure must have a particular interesting light matter interaction when the light is circularly polarized, and you can also make these spirals more complicated. You can make them not just out of one material, but you can make them again composites. And by doing so, you have a tunability of these resonances that determine at which energies the maximum of the dichroism sets in. And that dichroism is measured here by this Kuhn G factor. And you see here examples that these structures really have in a broadband and tunable way this kind of dichroism. And applications they envision are, first of all, you can create polarization filters that are extremely thin. You can make sensors. You can basically make a form of chiral chemistry possible. And we all remember that the chirality of molecules is very important. If there was this Contergan issue, for example, many decades ago, where the only difference in the medication was just the left or right-handedness of a molecule, which one of the two created this disaster, this birth defects. So it's very important, obviously. You can think about, and they realize by plasmonic ideas, single photon sources, and they can also look into nano waveguides. Photons in general are very good for quantum communication applications, and here we deal with chiral light, so to say. And an interesting aspect is also that if you have a free flying photon, you always have a spin momentum locking. So the spin of the photon is always parallel or anti-parallel to the propagation vector, the k vector. But that can be changed in certain plasmonic structures where the spin can actually be orthogonal to that. And you can play with these things as well with useful applications in quantum communication. Okay, these were the examples I have here from UNL. Don't know where I'm doing, how I'm doing in time here. Hopefully not too bad.
Thank you very much. Okay, great. This talk is open for questions. That's it. So we have a question from Mark. Do you want to turn on your mic, Mark? Oh, I see. That's right. So, Mark, do you want to ask your question?
I was intrigued by your living transistor device, and I was wondering if there was any application for trying to build this in 3 dimensions and increasing the network capability of that device, kind of a biomimetic structure.
So
Yeah, it's just a small question,
yeah.
I know.
The honest answer is I don't know, but I chatted recently for a different reason with Ravi, and his enthusiasm and his vision make me think that he probably thinks in this direction. I wouldn't be surprised if we would try that, but I don't know the real answer to that. Certainly interesting, yeah.
Do we have any other questions? If I could make one comment, I thought one thing that was particularly fascinating was that you were using MEMS devices to do calculations, which is an interesting twist on, or maybe going back to the past with mechanical adding machines, but in this case, a much more complex kind of thing. Acting as a neural network. I thought that's very
so again, I'm of course not the expert in this, but I look at it a little bit as similar to what people now look into synchronizing oscillators, right? So if you couple them, and you know, when you come from physics, you can have the standpoint that pretty much everything of interest can, in one way or the other, mapped onto coupled oscillators, right? From splitting of energy levels in molecules, it's somehow all a coupled oscillator. And if you then introduce nonlinearity, as he does here, then it's not too surprising that you can do very complex things in principle with that. So he can basically mimic neurons, right, and couple them mechanically.
Thank you, Christian. Thank you very much.